Okay, so at this point we know quite a bit about what types of indexes MongoDB supports, how to create indexes, and the importance of indexes for the efficiency of our application. What I'd like to do now is walk through an example that gives you an idea of the type of thinking you need to do when you're designing your indexes. The goal is that our read and write operations are as efficient as possible. But as with so many things, this requires some upfront thinking and some experimentation. To be sure you've got the right indexes in place, what you'd really want to do is test your indexes under some real-world workloads and make adjustments from there. But that's outside the scope of this course. What we're going to look at here is some of the initial thinking you can do to get ready for some of that real-world testing. So what we're going for here is a selectivity of our index, and to what degree, for a given query pattern, the index is going to minimize the number of records scanned. And we have to consider this in the scope of all operations to satisfy a query, and sometimes make some trade-offs. So we'll have to consider, for example, how sorts are handled. Okay, so let's go through our example. And again, this is really the tip of the iceberg in terms of designing a set of indexes, but it gives you an idea for the type of thinking you're going to have to do in order to get those indexes right. So to think about building indexes that can handle our query patterns efficiently, let's return to our student dataset. Now in this version of the dataset, I've added a field for final grade, and we're dealing with about 1 million students. So here's the query that I want to look at. And the reason for this is because it illustrates several of the issues that we have to think about in designing our indexes. So note that what we're doing here is a query for all students with an ID greater than 500,000. Okay, so that's going to be about half the students. And records for the class 54. There's about 500 classes represented in here. And then finally, we're going to sort in ascending order on student ID, the same field we're querying on here. Now, throughout this example, I'm going to be running explain on the cursor that the query returns to us and specifying that I want to see execution stats so that we get nice detailed output about exactly what MongoDB did in order to satisfy the query. So let's run this. Okay, so I want to draw your attention to a couple of different things. So first, let's take a look at this, total keys examined. This is how many keys within the index MongoDB walked through in order to generate the result set. The result set, on the other hand, is only 10,000 documents. So we had to look at a lot more index keys than we really needed to in order to find the documents. What this means is that the index that was used in order to satisfy this query wasn't very selective. And you remember that selectivity is one of our key goals when we're designing an index. So let's see if we can figure out what happened. Okay, now when you move above execution stats in the explain output, the thing you're going to see is the output from the query planner. So starting from the top, working your way down, you've got a winning plan, and then you also get a chance to see the rejected plans. So this is, in JSON form, a specific outcome for this idea here, racing a couple of different query plans against one another. Okay? So what happened here is that the winning plan used a compound index based on student ID and class ID. And the losing plan, there's only one other, would have used an index based on class ID, but then it would have had to do an in-memory sort. That's what this component of this particular query plan means. Anytime you see a sort stage in a query plan, it means that MongoDB was or would have been unable to sort the result set according to the sort specified by the query in the database itself. Rather, it would have had to do an in-memory sort. So what happened here is that the index that won is one that was able to return sorted output. So it only had to get to that certain threshold number of returned results, which is, I believe, 101 returned documents, versus, if you remember, 10,000 documents would have to have been returned by any query plan that was unable to do a sort within the database. Okay, because we actually were able to identify 10,000 documents that match the query parameters stipulated here. Again, the issue was one of selectivity, and the problem here is that we're specifying a range query that just isn't very selective. And so we end up touching every single key in this index that has a student ID value greater than 500,000. So that's about half of the records here. Now, I'm sure you can see where I'm headed here. It's this query, the point query, that's going to be considerably more selective for us. Okay? So as I said, there's only about 500 classes represented in this data set. And now, granted, there's lots of students taking those classes, but this is going to constrain our result set. And this is really what leads to those 10,000 records being returned, as opposed to the 850,000 that were identified. So what would be better, given the indexes we have, is if, in fact, we use this particular index, because this is going to be substantially more selective. So let's do that. Now, MongoDB does provide a way of forcing the database to use a particular index. I can't stress strongly enough that you should use this with caution. It's not something you should necessarily make part of your deployment, but it is a way of overriding what would be the outcome of the query planner. So that is called hint. Okay, and with hint, we can specify a particular index that we'd like to use, either by specifying its shape or its actual name. In this case, I'm just going to specify its shape, and what I'm going to do here is I'm going to say, okay, I want to use the class ID index. Okay, so let's see what happened with this query. Okay, we're now down from having scanned 850,000 index keys to just about 20,000 in order to get to our result set of 10,000. Okay, and the execution time is only 79 milliseconds, as opposed to the 2,600 milliseconds we saw before using the other index. Okay, now the fact is, what we'd really like to see is that n returned is in fact very close to total keys examined. So one way of addressing this is to design a better index.